This is instructional video number 40 in a series on arithmetic, algebra, and graphing. I'm Bill Kinney. It's part 9 of a sub-series on exponents, roots, and logarithms. In the last video, we looked at what it should mean to raise a number to a rational power in this way, positive rational power like that, and then a negative rational power based on this definition and the fact that I know what it means to raise a number to a positive rational power. I guess I can fill that in more. This can be thought of as either this or this. Those are going to be equal to each other. I also briefly talked about what it means to raise a number to an irrational power via successive approximations to that irrational number that get better and better. Again, it doesn't mean you're going to know how to calculate it in any sense by hand. You have to have the technology, but at least the idea is definable. And we saw that 2 to the pi power ends up being approximately 8.8249778727, though I'm sure it's an irrational number. I'll go ahead and write that in here. Approximately 8.824977827. All right. In this video right now, I want to focus on summarizing all the properties of exponents, ones that we've talked about and a few that we haven't really talked about. And if we have time, then I'll also start at the logarithms, so that we can hopefully wrap up this video sub-series in the next few videos. So what properties? The one I've focused on the most is this one. Right there. B to the m raised to the nth power is the same as b to the m times n power. Order of operations, here you do the b to the m first, get a number, then raise that new number to the nth power. Here you'd multiply m and n first to get their product, and then raise b to that product power. You get the same thing either way. That's what the property says. Another one that I mentioned is if you've got this, meaning figure out b to the m and b to the n, and then multiply. Order of operations, the exponentiation, the powers get done before the multiplication. That's the same thing as doing this. And in this notation, you do the addition first. It's in the exponent, do it first, figure out m plus n, and then take b to that power. You get the same thing. Here are a couple other properties. I may have mentioned this one, I'm not sure. If you take b to the m divided by b to the n, that equals b to the m minus n. That'll make sense with simple examples. For example, 2 to the 7th divided by 2 to the 4th. Well, what does that mean? It's 7 2's up top and 4 2's in the bottom. All 4 2's in the bottom divide out with 4 of the 2's on top, leaving you with 3 2's on top and a 1 on the bottom, which is the same as 2 to the 3rd power, 8. By this property here, that's the same as 2 to the 7 minus 4 power, 2 to the 3rd. It's a shortcut. We don't have to write these out and then do the dividing out. We can just do this. So it makes sense in that simple case. Turns out it makes sense in every other case. M and n here, by the way, b is going to be a positive number when I write these things. M and n can be anything. They can be any real number. That's pretty amazing. Even irrational numbers. Takes a lot of proof with the irrational numbers, but it's true. And then one more that I haven't written down before is that if you've got two different numbers, a and b, being raised to one common power, turns out by the commutative property, really, you can write it this way. You can raise both numbers individually to that power m and then multiply with the results. Here the order of operations is to do the product first and then the exponent. Here the order of operations is to do the exponents first and then the product. That's another property of exponents. In all these things, you really need more practice with it than I'm giving you here in just watching these videos. You should make up your own examples. You should test these things until you feel like they make sense to you, at least when m and n are integers. And you want to get them sort of in your soul, in your mind and in your soul, so that you can use them whenever you might need them. They are all useful. Alright, I think I've got time to introduce logarithms. And we're going to use a real-life problem to try to motivate them. A population of my favorite bug, mosquitoes, haha, just kidding, is growing by a factor of 10 every month. Two questions. How long until the number of mosquitoes grows by a factor of 10,000 and by a factor of 40,000? Now, I have no idea about mosquito population growth. I just made this up just to be sort of funny. You know, you might imagine mosquitoes do reproduce very fast. So it's growing by a factor of 10 every month. We can certainly answer this first question pretty quickly. Maybe you pretend there are, again, it doesn't matter what you pretend, maybe you pretend there are 1,000 to begin with. What does it mean to grow by a factor of 10? It means you multiply 1,000 by 10. So after 1 month, there'd be 10,000. I want to answer the question of how long until the number of mosquitoes grows by a factor of 10,000, not how long until the number of mosquitoes is 10,000. So it's 10,000 after 1 month, it's grown by a factor of 10. After 2 months, it will have grown by a factor of 100. After 3 months, by a factor of 1,000. After 4 months, by a factor of 10,000. The answer to this first question is 4 months. It will have grown from 1,000 to 10,000 times more than 1,000, which is 10 million. It's also the same as 1,000 times 10 to the 4th. The exponent is the answer to the question. How long will the number of mosquitoes grow by a factor of 10,000? Likewise, I want to figure out how long will it take for the number of mosquitoes to grow by a factor of 40,000. The exponent will be the answer. I'm going to write the exponent as an unknown x. How long will it take for the mosquito population to grow from 1,000 to 40,000 times 1,000, which would be, what, 40 million. The exponent is the answer, whatever that exponent is. Let's simplify this equation. I can divide out the 1,000. I can divide both sides by 1,000. Thousand divides really with this 1,000, leaving you with the 40,000 to begin with. What I'm really after here, and this emphasizes the fact that the starting population is irrelevant, is I'm after what exponent will make this true. Now once again, you could experiment with your calculator. If you think about it, the answer's got to be between 4 and 5. Try 4.5. Too small. You could keep experimenting until you get the right answer, at least a good approximation. Getting pretty close there. Looks like the answer is going to be 4.60 or something. Close to 4.602. Calculators have another feature built in, usually, that makes this calculation of what x is much quicker, at least in the case where you've got a 10 there, as we do. There's a log button right here. If I press that button, log, and then type 40,000, that's going to give me my best approximation for the answer as quick as possible. 4.6020599991. If I take 10 and raise it to that power, the calculator is probably going to approximate it to be exactly 40,000. Yep. Again, it's keeping more digits of accuracy. I'm sure this is an irrational number, not rational. If I truncate it there, it's a pretty good approximation. So the answer would be about 4.6 months. If the month was 30 days, 0.6 months would be 18 days. So about 4 months and 18 days is how long it would take for the population to grow to 40,000.